For homework
You
four,
with the hand up. Yes.
Question 9. Is there going to be anything like this on the exam? Because I know my calculator was having none of it for some reason. I put it in my calculator like 80,000 times, like in 80,000 different ways, and I couldn't get anything close. But everyone else seemed to have no problem.
Well, we had to evaluate the integral, so I guess the question is, are we going to have to actually evaluate integrals
Yeah.
on the test?
Yeah.
And that would be using
Yeah, apparently Desmos worked for you, right?
I just used my, I
Oh,
just
for you?
solved
Yeah.
it.
Did
I took
anybody
the
go out to that
anti-derivative.
online, what's it called?
Wolfram?
Oh, what?
Wolfram Alpha?
Yeah, Wolfram Alpha.
I didn't use it. I just used my calculator.
Yeah,
Because
because
my calculator, most calculators can do definite integrals, like the graphic.
I kind of vaguely remember.
Can they actually, you can actually just put it in?
On graphic
This-
calculators can do definite.
I gotta do definite on there.
Calculate. Answers for number 9.
Oh, okay.
Because I vaguely remember on, and it might have been this problem, I'll try to
Okay,
go back.
so it's that, okay, so I don't actually need to evaluate it.
That it says you can either use,
Okay.
whatever you called it.
Wolfram Alpha.
Wolfram Alpha. Or, here's an easier way.
Okay.
And so let me try to look at it. I'm going to get you guys started on an exercise. And then we'll talk a little bit more about the exam for Friday. So then while you're doing that, I'll look at this.
Okay.
So why don't you leave it right there?
That happens like every day. Somebody walks in and thinking it's their class.
Yeah, early on in the semester, I went
You went to a different?
I went to the first floor.
Yeah.
Went there and I said, this doesn't even look like the same classroom. It wasn't. Okay. Where did I put that? Right here. So here is what I am suggesting we do in the way of a review. And this isn't comprehensive. This is just 4 problems here. 2 of these are derivations. You can use your textbooks. You got them. This first one, I copied a section out of, it's on pages 107 and 108. I copied this and worked together. You know, I want us to see how, if we can solve these 4 problems before the end of the period here, or at least dig into all 4 of them a little bit. So problem 1 and problem 2 are really kind of using, just looking at the derivation. So in problem 1, you basically have from the text how they get to the derivation of equation 4.45. Delta G equals nRT time the natural log of the final over the initial pressures. Okay? Basically what I want you to do right now is derive an equation for delta A, using that as a template. But for delta A, it says the volume varies, not as temperature. In 445, it says the pressure varies. Okay, so that's the derivation.
What is delta A again? What's it called?
That's the Helmholtz energy, and it's a German term, Elbeit, which means work. It's the one energy term that's most related to work. That energy is the maximum amount of work you can get out of something. So A is related to that. So use your books and kind of work down through there. And number 2 is derivation. What is the delta S with respect to delta S over delta V at constant T for a gas that follows a van der Waals equation. And number 3 Well, I'll tell you a little bit more about number 3 in a minute. And number 4 is a derivation, too. So 1, 2, and 4 are derivations. And on number 4, you can use example 4.5 as a template. You can see what they did on example 4.5 and try to work through that to derive that equation. All right, so why don't we take 20 minutes, 30 minutes and chug on through some of these as best you can, and then we'll talk about them. I'll pull them up here and we can, so, let's see, smooth. Okay, on number 1, this is what they're calling these natural variable equations for each one of these energies, A, U, G, and H. And so if you really wanted dA, well, you could get to this equation. Oh, it's not on. Why not?
I just got 0 equals n.
Well, that's not plugged in.
It's not plugged in?
No.
Oh, you're right. Right, okay. Apparently someone else is using this.
There.
And this thing is putting a lot of pressure on there, so let's hang that up there. There we go. All right, so you can get to this point. So if you have just kind of the full integral of this, or not the full derivation of this, so dA is going to be the partial of A with respect to t at constant v dt, and then that gets you to these more or less Maxwell relationships. This is the same. This is the same as that. So that's minus S and the partial of A with respect to volume at constant temperature. That is the same as that. So it's minus P. So this is a good starting point to solve number 1. Here's the good starting point for solving number 1. So basically this can be, if you break this apart, is minus P dV. So if you take this out of the denominator, constant temperature, you got the dA equals minus P dV. If you integrate both sides of this is going to be delta A. This is going to be minus P dV, and as I overheard Ryan saying, P equals nRT over V. So we can substitute that in there. So this is negative nRT dV over V. All right? And so the integral of dV over V is going to be the natural log. So this is going to be nRT, those are constants, times the natural log of V final over V initial. All right, so you end up with a similar equation as 4.45, but now for delta A.
So we can just assume in all these derivations that PV equals nRT is always going to work?
Well, number 2 is actually taking you to a van der Waals.
Well, yeah, 'cause it's like specifically says, but like, how are we going to know?
It says right here, it says here.
Oh, does it? Well, like, this wasn't like an actual question.
Okay. Does it say it in there? Consider...
I think in the question it doesn't say, but like.
In similar
further down,
fashion,
it
right.
talks about
Okay.
You gave us an example that talks about ideal gases.
Yeah, I don't know if the test specifies that. It probably will call it out as a real gas, or that you need to use the Van der Waals expression. But for the most part, yes, we'll assume ideal gas behavior. I think most of the chapter was kind of that way. Okay, number 2, just remember that you can get to there's the Van der Waals equation, essentially, solving for pressure. What is the delta S with respect to V at constant temperature?
Okay, so through Maxwell's relationships, we can figure out that's equal to negative dP over dt. But then what do we do from like
What, that this is what?
There's
so
no negative in the textbook on that one.
oh then
What do you got? Partial of P with
Or-
respect to,
partial p with respect to t.
Yeah, for the partial P respects T, constant volume equals ds dv constant temperature, that one.
Okay.
Is that the one you're using?
Yeah.
Well, I mean,
I
I
have
don't know
two
if it
negative
looks right,
signs on
but-
mine, but they might be.
I mean,
I
yours
should-
might be right.
Check the book.
let's see, where, Ryan?
Oh,
What page is
yeah.
that?
Is in the first term, is the denominator B
101.
minus NB?
I think you're right. Yes. Yes. Thank you.
Oh, I had a negative sign for both.
What page are you on?
No,
Dominic?
I figured it. It was mine. I had a negative sign on both sides of the equation, so
Oh, okay.
it was correct or incorrect.
So, okay, all right. So if you differentiate this, differentiate that,
Oh, with respect to t at constant v.
yes.
Wow, this stuff making more sense. Wait, you only have, what are you talking about?
And count the pixels in that.
Yeah. Only one negative.
This is different. This is different.
That is, oh, it is different.
Okay, so what is the derivation of that expression with respect to t at
NRT
constant
over
v?
B minus NB.
And R.
Yeah, get rid of the T. Just NR over.
Wait.
Yes?
Yep.
Yep.
So now what we have here is this,
Yes, we do.
okay? And Dominic asked, is there some sort of template for this? And the template is example 4.7 in your text. Okay? Okay, let's go to the toughest one.
We haven't started yet. Should we start by ourselves first?
Yeah. Yes. Crunch through number 3. or start thinking about number 3. And I'll give you 5 or 10 minutes to wrestle with it, and then I'll give you a couple equations and a couple hints, and I'll let you wrestle with it some more.
The delta G equals R to the KP.
Which one are you doing? Delta.
G. We weren't getting delta G though, I don't think we're supposed to solve it that way.
Maybe this one, delta natural log of K over dt equals delta H of reaction over T squared.
Is it just K?
Because you have natural log of K.
Well, I like it. KP or KC?
It just says K, so this one.
Kaja and Dominic work if together or separately, however you want to work, but you don't feel like you have to be crunching through this all by yourself.
You know what Mexico's said. Mistakes.
What is this?
Something else.
Is that the magic school bus lady?
Yeah.
You know there's been a magic school bus show now?
No, this is broken states. Yeah, that's it. Something else.
Okay, I need to get over it.
Alright, we're gonna meet them, so.
Okay.
I'm gonna take a picture and bring it over here.
Alright, so first,
Wait, that might be Rula. Hold
so
on.
the expression for Ellen.
We don't have KC.
I don't know what type of word CP came from. I thought we left that in chapter 3.
What?
CP.
Yeah, I thought we left it in chapter 3, but it keeps
That
going
just
back
mean
to my
that we want an
guys.
expression.
We can also use this equation right here. We rid of that T.
So we don't have the temperature.
Yeah, but T on
The 1 over
T squared.
T?
So I think it's like.
Wait, what about T squared?
We can get rid of that and do derivative of natural log of K over 1 over T equals negative delta H over R.
Oh,
And then we
No, I'm not
have.
feeling it.
I'm not feeling it.
Oh, it's bad.
He's gonna pull up the Maxwell equation sheet. Let's do this.
oh yeah, I'm doing this.
No, you're
Okay,
not.
so,
There's a
So.
there's a CP equation.
delta G exists here.
Yes, it does. You are
All the
right.
way back to chapter.
I'm slightly concerned.
Yep, somewhere.
Where do we? Let's figure out what we do with CP.
No, I'm on testing it right now. You know it.
Hold on.
the Van Hoff.
That's what I'm thinking. No.
What is that?
Dr. Crane, when I was bringing up in Kenton, remember?
The
I
Van
can't remember anything that happened in Kansas.
Oh, I don't remember anything that happened. I just remember the Van Hoff Act. Because we didn't use it, so I stored it. We don't have to know this. I was like, oh, sounds good. Don't
So why you store it?
So you
I stored the
remember.
name.
Oh, you don't need to know
name.
this. Okay, I'll
Or
remember.
maybe go through your hard drive and pick out this bad stuff.
My brain deletes all the important stuff and saves all the useless stuff.
I'm not a corporate Sherlock.
Well, I've never watched Sherlock, so you probably copied me.
Wait, hold on.
Ooh, we can count. So delta H.
Oh,
Count delta H.
Squared.
No, but that's not delta H. Yeah.
We're just gonna derive an expression. So this one literally. How do we get KP in there? Oh, okay. Hold on. What if?
Are we going to integrate with respect to temperature?
Do some fancy stuff. I'm using Van Hoff. We're going for it.
What's your plan with that? Yeah.
Dude, you just have to integrate. It'll be fine.
Is that just the answer to everything?
Just integrate.
Is that the answer? Just integrate?
Just
To this day.
I mean, that's normally a good place to start for a lot of things, to be honest.
Which are your calculus?
Not necessarily, but
Calculus
that's-
still don't know.
Okay, we have 59 days to the last class.
Wow, countdown already?
Let me try that calculator.
Oh yeah, go for it.
I mean, we have to solve the expression, we have to solve it, so therefore,
Equilibrium.
doors
Yeah,
are
so.
wide open.
Okay.
Oh, you solving.
This would be easier if we had. Yes, so that does G.
We only have one DT.
Where's your
That's
exponential?
the issue.
Yeah. So it's this arrow.
We
Yeah.
use the OD 45.
That's a problem. Those don't work very well.
Oh, you trying to do E raised to something?
Yeah.
That's somewhere else. You have to hit the natural log button and scroll through. Yeah, this calculator is really old. Yeah, I can. Yeah.
Do you want to borrow my sister's calculator?
Then I wouldn't know how to use it. I know how to use this guy.
You can use both
Well,
of them.
yeah, do you? Do you really?
Yeah.
You have to use the internet.
So
I just did it on this cheap,
Guys,
$12
Your
calculator.
preferred differential equation. We know the form.
on this guy.
Yeah, I just did it on this calculator. This is a TI-3, TI-30.
So yeah, it's supposed to be.
Yeah, so we have ln of k.
He was 150 the first part.
Okay.
So
So this is 9
Right,
times
and
10
then-
minus
so
30,
then-
or 0.009.
Why we solve
150, and then it's 1 minus that.
Now, the last one here is squared. Okay.
Okay, so but it's 0.009 times 150, and then it's 1 minus that number.
Somehow that falls out of here.
The 1 minus.
Yeah,
Okay, because that would definitely explain why I kept getting the wrong answer. 'cause it
yeah,
doesn't count.
I think that falls out of there.
Yeah. Now, why does it?
And then, but you keep the -1 at the end. We did.
Yeah, because it's with respect to EP, and that's constant.
Okay.
So, you got a 1.
To get
A 1 minus a 1. Yeah.
Yeah, because
see,
I have the same thing. I have 1 minus.
So
So how would you go from?
that falls out of it, the 1 falls out of it.
So it's just negative.
Yeah, it's just this
I
and
guess
that.
for this one,
Okay.
it's just
That will probably give me the right answer.
Okay.
Oh, I
This
see.
one,
That.
yeah,
Okay,
yeah.
not
Because then
this.
we can get rid
Invalid
of these.
input.
Hey, here's a stupid question.
Sorry, I'm trying to figure out how to solve the differential equation.
I know, it's about,
I took that off the line.
it's about that.
What?
Okay, let's look at number 3 for a second. And so derive an expression for the natural log of Kp. Well, first, you need an expression for this. You need to know a delta H at some other temperature. And so, yeah, because you're going to derive an expression for ln, you're going, so the second part is you're going to need this equation.
So we need, the first part we're going to need to use, no.
Okay, so
So do
you
we
want to
look
get
up?
to this expression, but to solve this expression, you need to know what delta H at any temperature would be. You need an expression for it.
Or delta H.
Yeah, so the d delta H at this temperature, remember delta H equals Cp delta T. And I don't have an equation number for that. That's actually back in chapter 2. So-
2.32.
What is it?
2.32.
Equation 2.32. So then you from there you can get to this expression. And if you integrate this side of it, you get delta HT naught equals, now you have an expression for delta CP up here. So here's your delta CP. Okay, so whatever you get here is going to go up into here to complete that.
What does that delta HT stand for?
Well, that would be the change in enthalpy at some new temperature other than 298.15 degrees. This is a little confusing, Dominic. I mean, we got the naught on there,
Okay.
which implies or suggests, you would think, that we're not talking about, we're talking about a specific temperature, standard temperature. But there's your delta H, there's your change in enthalpy for that reaction at standard temperature.
Okay.
Negative 84.48 kilojoules. So this is going to be, what is the change in enthalpy for that reaction at some other temperature? We have a heat capacity that is temperature dependent. A lot of times we say, assume heat capacity is constant. But here we're saying, no, don't assume it's constant. It is temperature dependent.
Don't forget plus C, please.
Yeah.
Can I see your solution for this one again?
That's what it's stuck at.
Yeah, I think
Will you know that 0 to 298?
Yeah, so this could be, here's your T naught to some other T. T naught being standard temperature, or 298.15.
So what is that final T then?
This T? Any T.
Oh, okay.
See, then you can plug in any T
Got it.
to that equation and calculate a KP. Once you have that expression.
So I broke it up separately. I just integrated that equation and then got my plus C. And I solved for my plus C.
Plus C means CP?
No, plus C. Anytime you integrate, you have to have a plus C. And
Yeah.
that's why we're giving you initial entropy and initial temperature. So we can solve for the plus C. Right?
Right. You're getting there, Grant.
We just haven't done this yet, so I was like,
Where do you have the C on?
I got
Delta H part or on the next one?
on the delta H part, I got negative 66,000. Yeah, that's right. Is that right?
Well, up in this part here, this C is going to be that.
Should be that.
Because when you're solving, even to, I have, this is the delta HT, so I can take my delta H, set right equal to, it has to be 10 to the third power. And then put it on temperature, and then you just have CO here, so you have to subtract this over.
Yeah, that's confusing. This isn't delta HT. This is your delta H at 298.15. Maybe we should take that knot off of there. And just the delta H.
But
temperature.
this is my, but at 298.15, this value is this, right?
Well, that's your that is your change in enthalpy at standard temperature.
Which is 298.15.
Right.
So this equation at standard temperature is going to equal out.
Yeah, but let's see, we integrate this here. This is going to be from like standard temperature to some
I think I
temperature
just
T.
figured it, it's all you do, right?
T.
is change the-
So that isn't going to be that. That isn't going to be that. That's going to be the change in enthalpy at this new temperature. And any temperature, whatever temperature T you define. So if you had delta, so if you change it, delta H equals this plus delta H naught right there. What do you get?
Yeah, so it's coming from that. Well, so.
Okay, you're putting in a T.
Oh,
Yeah, yeah.
Okay. so-
Okay, here's, what is that?
But I think, shouldn't you evaluate?
Yeah, I don't know. This is a little confusing, that delta.
I don't know, is that what?
This is your standard delta H.
What are they doing? Like,
This is going to be the change in enthalpy at some given temperature. Any,
Confused, how do you have a change in enthalpy at a temperature? If you're at a specific temperature, how is it a delta?
oh, okay.
Because at that temperature, you should have a specific amount, not,
well, because there's a reaction.
oh, the change for the reaction.
Yeah, it's the change in enthalpy at this new temperature for that reaction. All right, so enthalpy is temperature dependent.
Yeah. Like, I kind of get why you would just add it on the end at the same time, it doesn't make that much sense.
Well, see what you think of this here.
So there's a problem like this on the exam? Can we ever skip it though?
No, here, let me explain what might happen before anyone breaks out in hives. All right, you see this B down here?
Yeah.
What I think I may do on the exam, this was a potential problem on the exam, Part A and Part B. I'm more or less having you work out Part A right now. We're going to get an expression for the natural log of Kp right here, which is going to be needed to solve Part B.
Okay.
She's saying this might be on the test.
Probably will be on the test. This problem will probably be on the test, but Part A will be solved right
So
now.
we will not have to like solve this on the test ourselves?
Right.
Or, yeah.
No. No, I think what I'll do on the test is I'll write in the expression that we derive right now
That would be awesome.
for ln of Kp.
Yeah, that'd be good.
Yes, Ryan?
Oh, just a quick question on this one. Could you just explain why you went from 4 times 10 to the next 2 times 10 to the negative? Otherwise, that makes sense.
It would be just.
Were you integrating? You went to a power, so you had that too?
So
What's positive power?
Yeah, do you integrate to the same power though? You end up at the same power?
Yeah. Right, okay, it didn't do anything over here, because this is the first column. Second column, 36 for the... I'm about to look up on the corner. Yeah, I must have taken that divided by 2. So this is still the natural log of phi, which is giving this number. Yeah, let me see. I don't know if I have the other sheet. Okay.
Close enough.
Hmm. Well, wait a minute, Grant. Let me see what number did you have? You had,
I had
Did you
negative.
erase it?
Yeah, I erased it. I had negative 66,000.
yeah.
Oh, it was right? Oh my goodness. Oh my.
That's right.
Well, you gotta write it out again.
Yeah, but they got
Okay,
this.
so that would
It's in there
be
twice.
the 1, 2. So
See.
it's like this pattern, because right now it's just the 1.
Those are two different things.
Like
This
this.
is,
So 3, add 1, 4.
this is a constant. So this is something that's given to us, and this is the constant. He's just calling that the constant. That's like saying plus
Okay,
C.
so whatever the exponent is, add 1. There's also zero.
I'm just
Over
gonna
here.
start
It's
so.
3 there first.
Yeah.
3 there's no x, add the x.
So
And I
don't
also
actually use
questioned that,
So
that sign right there. Would you keep that negative sign?
Yeah, 'cause you're integrating. Integrating.
Why did I take that out of there? Because, okay, that's t to the first. Okay, so we're not taking the derivative, we're integrating. So
Yeah.
it stays
Over
at-
we.
or you
Yeah.
And we're integrating between two temperatures.
Here we go, here we go.
We don't have two temperatures.
We're just giving, okay, so you don't, when we're integrating, we're looking for a plus C. It's just like anytime you take it like integral, and you have to find plus C of that integral, you only need 1 point to evaluate that. You don't need 2 different points. You only need 1 point.
So that's why he's taking that with
Because it's
that.
p.
Yeah.
So at this temperature, this is that.
Yeah.
Then you'd have q, and then you see.
Okay. Okay.
Well, it's good to know it works.
Okay. All right, well, I'll tell you what, let's not, here is the solution. It is detailed and complicated, and it is some temperature dependent.
Because I can do this if it's on decimals. I just
Oh, this is elementary.
And then the second part is basically algebra. Part B is just algebra with that equation.
And using the right equation, that you,
Well, because like we were.
oh, you mean the second part here?
Yeah, second part here.
Yes.
It's just that equation you wrote up there, just a bunch of algebra, and then we got it. Alright.
Yeah, I thought you were talking about this
Yeah.
second part.
Yeah, no.
Yeah.
Wait. Part B.
Part B will be on the test.
Oh, part B wasn't given. Oh, okay. I got it.
So on the test, basically, for under part A, I'll have this last line on this piece of paper,
Yeah.
okay?
Yeah.
Yeah, we're gonna.
And then you'll take that information and what they tell you, what it asks on part B, and solve part B.
So part B isn't asking for KP. KP is part A.
Well, this expression for ln of Kp is A. And B will be using that at a different temperature.
Oh, okay, yeah.
That's what I was just looking at.
Is that the C? Is that the C grant was talking about?
The HT naught thing? Yeah, that's just plus C.
There.
And we solve,
Because that's your plus C, and you know your enthalpy and your equation,
Yeah,
then
yeah.
it's E. You know your temperatures, you throw in temperatures,
Oh.
and you just solve them for that.
okay, so we're at HT. How did you get that? Not the H not T. So you do H not 0
With respect to T.
minus
Yeah.
CP.
Cancel.
Or CP.
DT cancels. So you take, negative 2. So negative. What is, this one is like negative? You're taking the derivative.
Derivative should be positive.
So I see how you can calculate
60, 64, 4.
the constant. You calculate HT.
What do you multiply R in? Or you divide by R? That's why that's wrong.
Oh, okay, yeah. And then you multiply by.
Because that's the enthalpy at a certain temperature, right? So you took the H not and then added the CP.
Yeah, verify that. You're going from this to this,
Yeah.
so that's
Where did
what,
it
negative 2
I
times.
feel like once you solve
Divided by
for
R.
this constant,
Is that,
you
get
go
that?
back to this equation up here and just plug in your temperature and plug in your constant.
It's going to be 2 times that.
Yeah.
But this and this, I get completely different.
They're the same thing. They're just different numbers.
Oh, because it's negative.
Yeah.
Okay, never mind. That makes sense. So that's what they did. He solved for this, then went back and plugged it in to find
I
this.
divided by,
That's another part of it.
So then we know the
I was
HT
trying to get
and put it into that equation
I
that I
think,
was
well,
talking
the way I
about.
got it was
And then
I
you put the
divided
DT.
this by, or divided this by R
So
first,
2 L1 KP?
and then I get this number,
Two L1
but not when I,
No, dude, that's
Multiply by
derivative.
two.
That's just in the majority.
Yeah,
Oh,
to argue that number.
Mhm.
You have to put all numbers
Then he just says,
Oh,
okay,
so
how does he
he
go
didn't
from
take the
the
derivatives?
KP to
so I think you
L?
used to multiply by
Yeah.
He
2.
figured he does the derivative of both of them.
So we got.
That's what it is.
Well,
That's what it
yeah,
is.
from here to here, you
Yeah.
integrated. So,
Yeah, so he got this, but just by dividing by R.
yeah.
And he called that, why is that, that's not derivative?
No, it's not sure.
This term is just.
Well, you need to get rid of DT stuff.
Yeah, I think integrated.
Now this is plus.
Okay, oh, you integrated it. Oh, okay, so you integrated it.
Oh,
Integrated.
No, what
You
you-
just
No,
multiply by negative 1 instead of, or divide by negative 1 instead of multiplying by
Just complicated, like all the different ages, but not. I
Yeah,
think I
okay,
kind of
'cause
understand
yeah,
why
we're
this one
doing
comes
the derivative.
Why?
Yeah.
So I negative
Right.
one, so it gets rid of
So-
negative or negative.
All of these are large. That's weird.
No, but you see, there's a T here and there's a T squared here.
Oh,
So
okay,
cancel out.
okay.
Cancel out. Then does he do the derivative?
Oh, good, good,
So
good.
then he does times
I-
negative 2
yeah. But I don't understand why would we divide this
squares.
So did you figure out how he went from DLMKP just to LMKP?
By integrating.
You just.
Yeah, integrate both sides. So you integrate that and get some KP, integrate all that.
Have KP.
Okay, so that's an integration.
Oh, we only have outline.
What?
Yeah.
Okay, so then he plugs in the KP.
Could we just do base E
And he
to
plugs
13?
in temperature.
7, and
And you
then
figure what C is.
Sorry,
Why do you
KP.
care what C is?
at
Oh, because we have to go back up here, because we need to define the expression for the rest of the cake. Temperature. We need to define C.
That's what I would have thought.
Gotcha.
So we basically do the same thing in both these spots.
So we should rewrite the equation.
You know that equation that looks like the Clausius Clapeyron equation but has k's instead of p's in it? It's
5.20.
5.20?
Yeah.
On page 134.
This
I'm
one?
just wondering, when you're deriving this equation, couldn't we in theory have just, since you're looking for like k, couldn't we have just solved this whole thing with the stuff we knew and just solved for k there? And then that would have been deriving it? Because we know, because we have the initial delta H.
Solve for K
Because
at,
we have a K, and we have an initial temperature. But what do we have, or do we use this for,
Oh my gosh, I forgot that. Obviously, duh. That makes okay. 'Cause I remember. Yeah.
well, they're going from this to that, right? Going from this.
like, could we just throw this delta H equation right there, and then just use this same, instead of doing this? Or wait, is that the same? No, it's a different equation. Or is that the integrated version of the equation? That might just be the integrated version, so it is.
Well, this is for a T1 and a T2. This is
Yeah.
for a T in general, right?
But if we have an initial T, then we can plug that in, and then we just have a random T in that we can change. I don't know. Because then you would have an expression for K, and you could just put in a T, and then you get a new,
Yeah, I guess I don't see the usefulness of this.
like, deriving the whole
This
thing.
equation. Yeah.
Yeah, because like, I mean, we did need the delta H, which we still have to derive that, but then this whole other derivation makes sense.
Yeah. Well, we have this.
Okay,
Well,
one
we
other
didn't have a delta H
question.
with respect to, like,
Does
oh, okay.
everybody have this book? I know I sent out a PDF, but does everybody have the book?
No.
I thought you had 3 books. I thought you had the PDF.
No, I just have the PDF.
You didn't have the PDF.
What happened to the other one? You return it?
You have it. I see 2 of them there.
Yeah, we will.
Grant, you have it?
Yeah.
So 3 of you have it. Okay. And then everybody has the PDF.
Yep.
All right. Well, I'll think a little bit more about this, but if I give this if I give this expression, then part B should be pretty straightforward.
We're on 4 now.
Yeah, let's do number 4.
Okay. Yeah, we have this. So there's a imaginary one here. So it's, yeah, 6, 6, 4, 4, 0, 2 squared. This stuff is 7, 9, 1. I don't know what that's supposed to be. T squared. Or the negative.
What are you talking about?
Integrating.
You're driving now.
Integrating.
Oh yeah, you're integrating, sorry. Well, the power's in the bottom, so you're ascending, so you're negative.
Yeah, how do you
one.
integrate when the power's in the bottom?
I mean, I do it now,
But you can just bring up power and then negative, because anything in
Oh.
numerical,
And it's
the top's
T
just
to the
negative.
negative two.
And then.
You
so
add
then
one,
you're
it's
gonna have
T to the negative
two,
one.
Right?
Yep, and so turn
The
the
negative
to the
bit out.
One.
Because you're adding one.
Yeah, you're.
But you're,
yeah,
the
adding-
number's getting smaller.
Because
So
it's
it's not,
technically.
yeah,
Yeah, so the number's getting smaller,
yeah.
but
One
you're
over
adding
T
one, then you
squared
divide by that
is
negative one. So
negative
yeah, you have to divide by what you're changing
two.
it to.
And then the other we're going to go through with this would be to add one, so you have T to the negative one.
And then you bring out the negative one. It's just
Oh,
Positive, so you have another over two.
This is something.
Just for fun.
Just for fun.
Just for fun, when we do this, would be students who make it more than the positive. And then T to the zero, so just make it more. Wait for that. No.
Consider natural effects.
Doesn't it become T to the zero?
There was the derivative of the natural of x over x, the natural derivative of the natural of x. And this one over x is the natural of x.
So that which would make sense if we had,
Well, it's this one. Yeah, A equals B. That's
Is there a lot of integration on this estimate?
No, I don't think so. I think that,
This is the extent of it for the.
yeah. There'll be differentials, but not very much integration.
Okay.
I think this problem is the one that used it.
because this would be 1 over T to the first.
Let me see.
We have some negative numbers here. If we take an antiderivative, isn't that really T to the zero rather than T to the first? Okay,
I think the reason why I can't go to T to the zero is that one to the zero is one, and you still one over one, and I don't think
and this will T to the
two
so
one over one.
anything to the negative first, that becomes a
negative S.
or anything to the negative first, that goes straight to the natural one.
I think you still.
Yeah.
Like,
Oh,
over
there should be
three
an
x
S.
squared, and then
I know. Yeah.
natural log.
They're on that. Yeah. I mean,
So I mean, that's basically what I was gonna do.
So there's something down there.
How do you
how do you get this? How do you do this?
Oh, they.
So the derivative of
The over is negative. Then same thing is for this one. So I don't know if that's correlated. They both equal pressure. But I don't know if we're both. Yeah. So this. Yes, that's what I thought. It's the equation that we
You will find definitely like that.
yeah, we need the T. Well, the T's here already.
I saw this for
What is dv
this equals
t?
this.
That is that equals u equals.
Oh, so that's
Yeah. Because then it's not really like much of a relationship. Like, writing about relationships, but
I don't know how to put it. The DHT. So I got any. Oh.
the craving 4.6. Oh yeah, 4.6. I got that.
But yeah, the question is like, why are we like keeping random things constant and it's okay?
Well, I guess because like in this one is called constant for T, and we're putting in terms of that, so maybe that's why it's called constant.
Oh, okay, yeah, okay, that's
Like, why is this not, like...
Why is T just staying there?
yeah,
then, like,
so
this
we
one.
got that,
We
that
take-
makes sense.
Yeah, so anytime, because we're taking the derivative of the whole thing with respect to B, and so we're treating everything's constant in there.
So if you're keeping the temperature constant, you can get rid of.
Well, no, we're treating,
Well-
we're just treating T as constant.
Yeah, you're treating, yeah.
It's like really, it's like 4.6, it doesn't look like 30.
Yeah.
So I feel like there's more sense to this than
I think there's like,
Yeah.
you take the derivative and then you just plug it.
you just
Let's plug this in.
apply new relationships then.
Yeah.
Okay. I feel like
Oh, okay, boy. Oh, we're running out of time.
There's no way I got it right.
Did you get this one? I mean, you just, partial U with respect to V, T, you can use partial of A with respect to V, constant temperature, plus T times the partial of S with respect to V at constant temperature. And then you can just substitute from these Maxwell equations, find substitutions for those. And you can show that this is negative P, and this is the partial of P with respect to T at constant volume. All right, I just put, so that's that equation I named after you guys. That's the Clapeyron equation. That's the Clausius-Clapeyron equation. There's one problem that has a derivation. I don't think there will be any problems that you actually have to integrate. You do for this part A of question 3, but I'll give that to you and have you carried on into question B. All right? 7, and if you want to get here early, you know, I usually get here about 12:30, 12:35. Just spread out and we'll get started. All right? And I'll see you Friday.
also got woodworking, 8 hours a day.